The given truss is a statically indeterminate structure. If we remove two members, for example, if I remove the member BF and DF, the structure becomes statically determinate to solve for the member forces. So the given structure is of double redundancy type. So I have removed two members BF and DF. Now the structure has become statically determinate structure. Now for the given loading and for this structure, find the member forces. Find the member forces, okay, and support reactions by taking the individual joints and drawing it as a free body diagram. Calculate the forces like this. So I have explained you already in the class. Do it. Similarly, taking the other joints, do it. Then prepare a tabular column. One column members, all the members, and in another column, member forces in all the members, which you have calculated so far. And since we removed the member DF and BF, you have to put the value as 0. Okay. Now, I told you we have removed two members, right? So that the structure becomes statically determinate. So in place of one removed member BF, introduce a unit force, remove all the external loadings, and find the support reactions and determine the member forces in all the members by considering the free body diagram at each and every joint. So calculate the force like this. So after calculating it, enter the values against the K column for this truss. For this truss, enter all the member force values against the column K. Now, introduce a unit load in the DF member, remove DF member, find out support reaction and member forces by taking the individual joints and enter in the column K dash, K dash. Now moving to the next tabular column and introduce a column L corresponding member length and PKL one column, PK dash L another column, then K square L another column, K dash square L another column, and another column is K dash L another column. Okay, after calculating this, sum the columns PKL, sum of PK dash L, sum of K square L, sum of K dash square L, sum of K dash L, and you have the equation here in terms of x and y, where x and y are the two redundants. Okay, summation of pkl, summation of k square l, summation of k dash l, and the summation of pk dash l plus y times summation of k dash square l plus x times summation of k dash l. Substitute all the values, you'll get two equations in terms of x and y. Solve for x and y. After solving it, so in this equation, for the individual members, you can find the member force S, which is nothing but the actual member force for the given actual statically indeterminate structure. For example, for AB, S for AB is equal to P for AB plus X times K for AB plus Y times K dash for AB. Find out and enter in this column. So like this, for each and every individual member, we have to solve for S and enter the values against the column S, which is the actual member force for the given actual structure, statically indeterminate structure. So moving on to the Castigliano's second theorem. In any and every case of statical indetermination, wherein an indefinite number of different values of the redundant forces satisfy the conditions of statical equilibrium, their actual values are those that render the total strain energy stored to a minimum. That is, partial derivative of a total strain energy with respect to the redundant force is equal to 0. Dou Wi by 2x is equal to 0. Let us solve a problem based on this. So the given problem is proper cantilever beam. At the free end of cantilever beam, we have one support. Let R be the support reaction. Then we take a section here. Okay, here at a distance x from the right hand, write on the moment equation. We know the strain and its stored equation due to bending, integration m square dx divided by 2ei. Okay, substitute here. And the differential partially with respect to r. Here r is redundant and equal to 0. Okay, then integrate, apply the limits. After simplification, you get R is equal to 3 by 8 WL, which is the support reaction force for the given proper cantilever beam. Then moving on next is this is the simply supported beam. Okay, simply subjected to UDL, WL by 2, WL by 2 are the two support reactions. I've introduced the one support exactly at the middle. Let that be R force. Okay, reaction force, unknown reaction force. Okay, now the beam becomes a continuous beam. Okay, so if you find the support reactions, WL minus R by 2, WL minus R by 2, at the middle you have R. Now take a section here at a distance X, write down the moment equation, you get this moment equation. Write down the strain is stored due to bending. Okay, two times limit 0 to L by 2, same strain is stored on either side. Okay, since it is symmetric. So then differentiate partially with respect to R, then integrate, apply the limits, you get after simplification R is equal to 5 by 8 WL. R is equal to 5 by 8 WL. Moving on to the next problem, you can see OS, OA, OB, OC. Okay, fix it at the top with OA, OB, OC. Okay, meeting at a point O where W is acting downward. So all the three wires are made of same material. Young's model is same area. So A is same. Okay, so we are now this W is acting downward and the forces acting, let P be the force acting in OE and Q be the force acting in OC and R be the force acting in OB, and all this PQR must act upward to balance the downward load W. Okay, let theta and beta be the angle. So we have found sine theta, cos theta, sine beta, cos beta, and resolve horizontally. So we get P is equal to 0.75 Q, and resolve vertically we get Q is equal to 4 by 5 W minus R. Okay, P is equal to 3 by 5 W minus R. Substituting Q here, so P is equal to 3 by 5 W minus R. Okay, that is we're trying to find P in terms of R and Q in terms of R, where I'm treating R as my redundant. Okay, it doesn't mean that always R should be redundant. I can keep Q also as my redundant. You have to find R in terms of Q and P in terms of Q. So I have to differentiate partially with respect to Q. Okay, here I have taken R, so I have to differentiate the total strain and stored partially with respect to R. So strain is stored due to axial loading S square L by 2AE. P is the force corresponding length, Q is the force corresponding length, R is the force in that member corresponding length 3 meter. So AE is same, I have taken outside. So P square and Q square R square. P we have got 3 by 5. Okay, Q we have got 4 by 5. Yeah, 4 by 5 W minus R. Okay, so square it and R square. Then we are doing some simplification here. Then dou W by Wi by dou R, differentiating it partially, differentiate the power, then minus R differentiation is minus 1. Okay, so R is equal to 7W by 12. So after finding R, find P. P is equal to W by 4 and Q is equal to W by 3. Okay, thank you.